We've seen the dramatic changes that can occur with stars as they age through their life cycles. We learned that low-mass stars end up as white dwarfs. We saw that high-mass stars end up as neutron stars and, in a few cases, black holes. But now we're in a position to examine each of these a little bit more in detail and see what the results can be. So let's begin with white dwarfs, the, again, remains of old low-mass stars. After they go through their cycle, they expel their outer layers, and this small, hot carbon object is remaining. This object has a very high density, and that is what allows it to be stable against the inward pull of gravity. These are also the cores of stars, and so they're exceedingly hot. They can easily exceed 50,000, perhaps 100,000 degrees. At these high temperatures, white dwarfs will give off much short wavelength light, such as ultraviolet light. In fact, sometimes we'll take a picture of a system where we think there might be a white dwarf, and sure enough, if we look at ultraviolet light, we'll see the white dwarf actually appear brighter than a companion star in visible light. We noticed its path, or its track, so to speak, on the HR diagram. After going through its various stages, the white dwarf ends up in the lower left of our diagram because we know it has a very low luminosity due to its small size and yet a very high temperature. So what ultimately will happen to a white dwarf if left to itself? It will just cool very, very slowly. It has so much energy stored within it, and yet it has such a very small surface area to release that energy that it can literally take billions of years to cool off. So, all through space, we do see a number of these very small white dwarfs doing just that. Interestingly, this hot remaining core, because of its high density, is about the size of Earth, and yet it compacts approximately a solar mass inside of that small volume. So again, you can imagine the tremendous density there of a white dwarf. Can these be of any size, any mass? No. Recall that these originate with low-mass stars, and essentially there is a limit to how much mass a white dwarf can have, and that limit is about 1.4 times the mass of our Sun. Well, this limit to a white dwarf's mass can result in some interesting consequences. Again, if the star is left to itself, really not a lot's going to happen besides cooling off, but what if we were to have a white dwarf star that was part of a binary star system that we saw earlier in our course? In other words, we start out with two main sequence stars, and one of them evolves through its stages and becomes a white dwarf. What can happen there? Well, in some cases, as its companion star now swells to become a red giant, the white dwarf's strong gravity can literally pull matter off the companion star. This would result in the mass of the white dwarf increasing. Essentially, what happens is its gravity is able to remove some of the matter from its companion and transfer it to the white dwarf. Now, normally it doesn't directly fall onto the white dwarf, but it can circle the white dwarf in what we call an accretion disk for some time before landing on the white dwarf. Those accretion disks often will get very, very hot because there's a tremendous amount of friction as the matter is slowly spiraling down onto the white dwarf. But for our purposes, the essential point here is that the mass of the white dwarf can increase. In fact, in some cases, it can increase above that limit of 1.4 solar masses. What will happen then? Well, remember, this is the core of a very hot star. Gravity is very, very strong here. It's only being supported because of the high density, but when enough matter is dumped onto it, gravity now assumes the upper hand and once again starts to contract our core. Well, it contracts it enough that the temperature begins to skyrocket and fusion begins, but here's the point. There is no star surrounding the core to contain the fusion, and as a result, that entire small object is going to explode catastrophically in an incredible explosion that is a different type of supernova. This is a white dwarf supernova. Now, to distinguish it from the supernova that we discussed in our previous lecture, where a massive star's core collapses, we're going to designate them, as astronomers do, a type 1 supernova. That's our white dwarf exceeding the 1.4 solar mass limit, and the entire object essentially fuses explosively with nothing to contain it. Our massive star supernova, on the other hand, is designated as a type 2 supernova. Here you'll recall we have that iron core contracting and collapsing. All the outer layers collapse and bounce off of the core in a titanic explosion. These eject essentially roughly similar amounts of energy, but the white dwarf supernova actually can emit more energy. We also will notice, if we were to observe both types of supernova over weeks and months, that there would be a little difference in the way that they shine. The white dwarf supernova would peak at a little bit higher luminosity and then decline a little bit faster than our massive star supernova. So this is how astronomers can see a single supernova explosion and essentially determine which type it is. Another way they can determine that is if you consider for the moment that a white dwarf, of course, has no hydrogen in it, does it? And so if they were to see a supernova and take a spectrum of the supernova and they did not see any lines of hydrogen, those spectral lines we've discussed, that would indicate it's likely a white dwarf supernova. On the other hand, our massive star, or type 2 supernova, does have an immense amount of hydrogen surrounding its core, and when it explodes, its spectrum would show lines of hydrogen. So this is essentially how we can determine the difference between the two types of supernova. So interesting that although a white dwarf left to itself will just only quietly cool, a white dwarf in a binary system can easily attract enough matter from its companion to go over that limit and explode as a type 1 supernova. Well, now let's go back and discuss neutron stars. You'll recall those were the extremely dense, extremely small cores of our massive star, or type 2 supernova. And here the density is even far higher than that of a white dwarf. Here you have more than a solar mass packed into a sphere only a few miles across. Extreme density supports this from any further contraction. How is that possible? Well, we explained that as this occurs in the supernova, the electrons are crushed inwardly to the core of their nuclei, where they combine with protons to form neutrons. And as a result, we have an object with essentially no space within it except for these extremely dense neutrons. These objects are even far smaller than a white dwarf and even far hotter. And as a result, they give off hardly any visible light. So if we wanted to study them, it would probably be a good idea for us to actually look for them in a very much shorter wavelength type of light, perhaps ultraviolet or possibly even X-ray light. And we do have a few images of such objects, although they're exceedingly difficult to see because of their small size. Well, being a very interesting type of object, we'd love to know more about them. How can we do that if they're so visible, so difficult to observe? Well, interestingly, back in the 1960s, a discovery was made that has enabled us to learn more about neutron stars. At that time, a young female graduate student named Jocelyn Bell was working with her professor using, at that time, kind of a newfangled radio telescope to search the sky and see what might be found out. And she came across a source in the sky that was giving off very regular pulses of radio light. Well, this was very intriguing. We didn't really know at that time what it could be. Essentially, what we found eventually to be the case was that this was a neutron star. Now, how can that be? Well, again, think about a neutron star being a very small object, but didn't it originate with a very large object, a supergiant star? Now, nearly every single star is going to rotate at some rate. And so when our supergiant star is rotating slowly, we had mentioned very briefly at the beginning of our course that an object rotating slowly, if it were to shrink, would need to conserve angular momentum. In other words, you could think roughly as the amount of spin it has. But if the size of the object decreases, the spin rate must increase. And here we have an extreme example of this. An enormous supergiant spinning slowly will result in a tiny neutron star spinning furiously after the supernova explosion. Well, think too of the fact that nearly every star has some level of a magnetic field to it, being churning hot gases and so forth. And once again, think about an enormous a supergiant star with a magnetic field. And as it contracts, is compressed, that magnetic field is greatly concentrated into that small neutron star. Now you might know magnetic fields have a north and south pole to them. Well, picture then for a minute this very small, compressed, quickly spinning neutron star with a very powerful magnetic field. It turns out that detailed calculations tell astronomers what this object will tend to do is it will tend to shoot energy or radiation away from its north and south magnetic poles. Now normally those magnetic poles are not necessarily lined up with the rotational pole. In other words, we would have our little neutron star spinning very, very rapidly in this manner, but frankly its magnetic field may well be inclined at an angle, and as a result these extraordinarily powerful beams of light or energy will sweep essentially a circle out into the distance. Now normally we might not notice that if we were observing the neutron star from the side, but if we happen to lie in just the right direction, we might look out into space and notice one of these beams of light sweep right over us. In other words, pointed directly at us. We would see an extraordinarily bright pulse of light. And as that neutron star rotated very quickly, we would see that pulse, again, align with us very, very quickly. We would essentially observe what Jocelyn Bell saw, pulses of light, whether they be radio light or visible light or other types of light. So this actually turned out to be an observation of a neutron star. Again, it'd be very much like perhaps a lighthouse. Maybe you've seen that where the beam is sweeping around, and if you're standing in just the right position as that beam sweeps over you, you're going to see a very bright pulse of light. So pulsars are the term we use for neutron stars that happen to aim their beams of energy at us. This has allowed us to learn more about them. It turns out that just as a white dwarf had a certain limit to its mass before it underwent, again, catastrophic fusion, neutron stars also have a limit to the amount of mass they can contain before they'll undergo a very dramatic change. Now that mass for a neutron star is approximately 3 solar masses. So again, we might normally think of a neutron star left to itself. Nothing's really going to change. It's going to last a long, long time cooling off. But what if our neutron star happened to be in a binary system where, once again, it could pull matter from its companion and increase its mass? What could happen then? Well, if that scenario were to play out, that neutron star might at some point go past the 3 solar mass limit. Now gravity is strong enough to overcome and crush even those incredibly dense neutrons, and the collapse will resume. We mentioned briefly in our previous lecture, this will crush that object down with nothing to stop it. And essentially we form a black hole. So what is a black hole? Again, it's not necessarily a physical, tangible object you could somehow touch, no, but it's an incredibly tiny point of incredibly great mass and incredibly strong gravity. How strong is the gravity? Well, it's so strong that not even light can escape the black hole, and thus the term black hole. So these are incredible results of the highest mass stars, again, either undergoing a supernova explosion or perhaps a neutron star in a binary system accreting enough matter to turn into a black hole. What can we possibly know about a black hole besides what our theory might tell us? It's true, they're extraordinarily difficult to observe. Essentially, they don't give off any light, do they? So we'd need to think of some other very clever ways to try to study black holes, wouldn't we? First of all, we might characterize them by describing their size. Well, again, the very center really has no size, but the farther you go from the center, slowly, gradually, that strength of gravity would weaken, and you would reach a certain distance from that center at which light could just barely manage to escape if it was present. Well, that distance, when you consider a spherical shape around the black hole center, that particular distance, we call that the event horizon of the black hole. In other words, if you were somehow within the event horizon, there was no possible way to escape. If you were outside the event horizon, it might be possible for you to escape if you could move extremely fast. Now, the event horizon of a typical small black hole, such as might form with a star, perhaps 3 to 5 solar mass black hole, would only be a few miles. So really, you'd have to be quite close to the center to be inside that event horizon. The actual distance itself from the center out to that event horizon is termed the Schwarzchild radius. This radius named after the scientists who essentially discovered this. And you can imagine that as the mass of a black hole were to be increased or get larger, well, that radius would increase. That event horizon would move outward. Now again, I stress this is not a physical surface. This is a distance from the center at which escape would no longer be possible. Why? Because you'd have to move faster than the speed of light, which is impossible. So we can begin to characterize black holes by their Schwarzchild radius, their event horizon. What's it like near a black hole? Well, I won't go into great detail, but you may have heard various things, and it is true that the incredible gravity here of a black hole has a tremendous effect on not only space, but even on time. Think of it. Near the event horizon, gravity has such strong effect that Einstein's theory of relativity tells us that time would actually slow down. What a remarkable, incredible effect. Now, you and I don't normally experience such a thing, and we probably never will, but near the surface or that event horizon of a black hole, time would slow dramatically. In fact, the gravity would be so powerful, it would pull so much more on one part of you than the other that it would stretch you out. So we certainly don't recommend going anywhere near a black hole. So can anything escape from a black hole? Not once it's inside the event horizon. As I mentioned, to do so, you'd have to move faster than the speed of light, which the laws of physics tell us is simply not possible. Well, what happens to anything that might be foolish enough to get near a black hole? If it was pulled into that black hole, it simply disappears, and you and I can have no further contact with it. There's no way to observe it. There's no way for it to somehow send out a signal. There's no way for any knowledge of what's happening inside the black hole. What happens to the matter, though? Well, essentially, the mass of whatever the object may be falling in is added to the mass of the black hole. And so essentially, a black hole can slowly, gradually increase its mass. Now, this may occur naturally if there's gas, dust, other material around a black hole that's pulled in. The black hole could gradually increase in mass, and in our future discussions, we're going to see some of the consequences of that. But essentially, as it falls inwardly, that material would be drawn to the center. Again, what's at the center? Well, we have a label for it. We call it a singularity. And to our best knowledge, our best theories tell us that no known force can resist, again, the incredible pull of gravity towards that singularity. So essentially, matter would be drawn into the black hole, would head for that singularity, and it would be crushed down to essentially an infinitely small size. The density would essentially approach infinite density. So very difficult for us to grasp these concepts, these very strange effects of a black hole. Well, you might say that's all very fascinating, and it is on a theoretical basis, but does this really happen in nature? In other words, do black holes really exist? Well, as always, we'd expect some evidence of that. We may not be able to directly see a black hole just yet, but is there other ways to know if there could be such a thing out in space? We would need to look for indirect evidence, wouldn't we? Remember, the black hole's gravity is very much a real thing to you and I, and it could have effects on other objects. Picture, for example, again, a binary star system. And at some point, a very massive part of that binary star system, one of the objects could go through these stages we've described, perhaps explode as a supernova, form a black hole, but that mass of the black hole would still continue to orbit with its companion star, depending on their masses. Now you might recall earlier in our series we discussed how astronomers can determine the masses of stars. You might remember that we discussed we need to be able to measure the distance between them, and we need to be able to measure the amount of time it takes them to orbit around their center of mass. So picture another star here orbiting our black hole. Our black hole is wobbling slightly perhaps because it's probably more massive, but of course we can't see the black hole, can we? So picture now, if we were to notice a star, essentially with some type of observation, orbiting around something invisible. Well, we could measure the distance of its orbit, and we could measure the time it takes, and we could go back to those equations that we talked about, and we could plug those numbers in and make a calculation, and we would of course come up with the mass of both objects. Now if we understood the secondary or companion star reasonably well, perhaps we recognize it as a certain type of star and a certain type of mass, we could subtract that out of the total, couldn't we? What would we have left? Well, we would have what's left is the mass of the invisible object. Essentially, if that invisible object had more than 3 solar masses, we would know it cannot be a neutron star, but would have to be a black hole. So this is one very powerful method that astronomers have used. By carefully observing different systems, we may see an object orbiting something that's virtually invisible. We can measure its motions and determine that the other object must be a black hole. Now, as those objects orbit each other, it may be that the black hole is able to actually pull matter off its companion. Some of that matter may get quite hot, and some of that matter that's very, very hot may give off a certain distinctive type of light, perhaps X-ray light or others. And again, calculations can tell us what that would look like. And if we were to observe that extra light, that X-ray light perhaps, where we don't expect it from the companion, we might have further evidence that there's a black hole there as well. So you can see how ingenious astronomers can be. Very interesting ways to establish and then confirm the existence of black holes. Well, we've again seen some very remarkable objects, haven't we? And now it's time for our summary as we discuss white dwarfs, neutron stars, and black holes. We saw that white dwarfs, of course, are the remains of a low-mass star after it goes through its stages. We saw it's a very, very dense object that, left to itself, will slowly cool. But if a white dwarf is in a binary system and is able to accrete or pull matter from a companion, it might exceed a limit of 1.4 solar masses and essentially explode as a white dwarf supernova or a type 1 supernova. Neutron stars. Again, these are the remains of very high mass stars exploding as supernova. Here we have tightly packed neutrons in a very, very dense small object, and once again, left to itself, would probably just cool very, very slowly. But if they were in a binary system, they could accrete enough matter to essentially turn into a black hole. How did we possibly get any observations of these tiny objects? Well, we saw that in some cases, the pulsar may be rotating in such a way that its magnetic field is going to aim very powerful beams of light or radiation at Earth, and as it sweeps over Earth, we observe that as what we called a pulsar. Finally, black holes we saw were the result of the very highest mass stars, again, going through those stages of forming a supernova. And here, the gravity is so powerful that not even light can escape. And as a result, you and I wouldn't see all that much, would we? How do we know that these are even there or possible? Well, we said we could look for indirect effects, couldn't we? We could observe carefully if we were to find a system where one other star that we do recognize appears to be orbiting something very massive and yet essentially invisible. That clearly would indicate a black hole. So what a remarkable end state we've seen here to the various stars of various masses. We really see a tremendous field of study here that astronomers have been able to take us into and tell us what happens to those little points of light in the sky. I think you can see we've learned a great deal about them in recent decades. However, you may know that all of the stars that we pretty much can see are part of our Milky Way galaxy. And this opens up an entirely new aspect to our research, our discussions. In our next lectures, we're going to begin to explore the Milky Way galaxy and then other galaxies. And eventually, we're going to conclude with a look at the entire universe. So I look forward to our next videos.